We want now to further generalize our approach to analyzing our equations and coming up with ways to visualize our functions and be able to visualize where we might be close to this issue of instability and close to areas where we might have too strong an oscillation and so on. So in developing these alternate visualizations, we start out just reminding ourselves of a couple of things. First off, in terms of our frequency response, we had noted earlier that if we apply a sine wave at the inlet point to our process, or as the manipulated variable time function, then we would observe in our output variable also a sine wave in a linear process, that is. So in a linear process, if we put a sine wave in, we'll get a sine wave out. That output sine wave will have the same frequency as the input sine wave, but there may be some shift in time for that output sine wave. So if we apply a sine wave at the input, it may take some time before we're seeing a pure sine wave at the exit side, but it will still then exhibit the frequency omega. So we had also discussed defining for ourselves an amplitude ratio or a magnitude ratio. And if we just go back here, we had said that we can consider that we are going to eventually steady out to some value, but that along the way, before the transient died out, that our process might go to unintended high values and oscillate to low values until the system eventually steadied out. And we had developed a way of estimating how high that maximum was going to be. And that turned out to be the amplitude as a function of frequency. So that was the amplitude to the sine wave in the response. And we had ways of estimating that. So we are going to further elaborate on that, and we are going to map out for a more generalized function. So earlier we had investigated that amplitude ratio specifically for second order processes and specifically for a sine wave input. We want to now consider the possibility that the process doesn't strictly follow some well-behaved second order system, that it might be more or even less complicated than that. And so how do we then estimate our magnitude ratio, and how do we estimate the phase angle, i.e. the time delay before it becomes a sine wave? And those are important dynamics features that we'll see are critical in helping us to develop and design our control system. So anyway, let's progress with that by noting that we have this important theorem, the basic theorem, as it's deceptively named, which tells us that the amplitude ratio or the magnitude ratio can be obtained if we apply specifically S equals I omega in our transfer function, and if we take the magnitude of that. So once more, we have this transfer function g of S, and instead of any arbitrary S, if we apply specifically I omega for S, and we will then get some complex number, and if we take the magnitude of that complex number, that will be the magnitude ratio at that choice of frequency. So that's one half of the basic theorem, and the other half says that that delay time, that phase angle, can be obtained as the angle of the result we get by applying I omega in G. So once more, if we apply I omega for S in G, we'll get out a complex number, and that complex number will have an imaginary part and a real part, obviously. And then if we work out the angle for that complex number, so if we take the imaginary part as the y value and the real part for the x value, then the angle that makes is given by arg. And it turns out that that angle will be the phase angle in our response. And this is a tremendously useful result or tremendously useful relationship And so we need to prove how this could be true, and then we'll go on to using it. Right, we've already said this g of even a pure imaginary number may have a real part. It generally will have a real part and an imaginary part. In polar coordinates, of course, we can express this in this way, that this complex number g of I omega will be the magnitude multiplied with e to the I of the angle of that complex number. And we can, of course, evaluate the magnitude of g of I omega as the square root of the sum of the squares of the real and imaginary parts. Then, of course, the angle likewise can be estimated as the arctan of the imaginary part divided by the real part. So all this is not yet getting into the theorem. These are all just reminders about the nature of complex numbers. So getting into proving the theorem right now, we are seeking these results, and we start with by noting that if g is our transfer function, then the output Laplace domain function will be the transfer function multiplied by the input. And we note that if we are applying s equals I omega, then in effect we are applying a pure sine wave as our input function, right? And that's elaborated here. We established earlier that if u is u over bar sine omega t, then u of s is going to be u over bar omega over s squared plus omega squared. And we can separate this out as s plus I omega times s minus I omega, right? By virtue of the imaginary number. You can see that if you multiply these together, it's s squared, which is there, and then s times minus I omega and s plus I omega, so the middle term vanishes, and then I omega times I omega is I squared omega, which is minus I squared times omega squared, which is minus omega squared, and then times that minus, and then that's plus omega squared. So this we know, and if we apply that now in our transfer function, we had said before that any transfer function can be written as the ratio of the product of the roots of the zeros. We can write that in terms of the zeros in the numerator and the poles in the denominator, and there will be some constant out in front here. So if you look at lecture 2, I think it is, we talked about how we can break a function down into this form. So whatever our function is, we can represent it in this form. And now if we go and apply that here, we've already defined what u of s is going to look like. So if we take y equals gu, so g times u, which is this, is going to look like all this, right? So this is the u part, and this is the g part. And then we can do partial fraction expansion here. So we can take each of these denominators, and we regard this as a constant. Well, these are constants out here. These are not changing in time or in s. These are just scalars. It's a lump of scalars. And so we can do partial fraction expansion. In other words, we can claim that there should exist a form like this, where if we take each factor in the denominator, then we can separate that as a new term, and we have these unknown coefficients a, b, c. So a and b to take care of this sine wave function here, and then c up to some constant, so a series of values here for each of the pole contributions. So these are all different terms here. And now if we don't have some kind of trivial omega like a 0 or something like that, then we can see that if we apply apply s plus I omega. So if we multiply both sides of the equation by s plus I omega, then that will be cancelled out here, and then s plus I omega will survive in all these terms. And then if we choose s equals minus I omega, so limit s going to minus I omega, that's going to give us s plus I omega times y of s. And in these other terms, we have s plus I omega in each of these. So applying minus I omega means that all those will zero out, leaving us with just a here. In other words, a equals y times s plus I omega, where the limit for s is going to minus I omega. So it looks like that. So that's how we get a. And if we apply this, if we multiply y of s by this, right, looking at y of s here, we can see when we multiply by s plus I omega, then this factor vanishes. And then if we set s equals minus I omega, then we get minus 2I omega here. And all the other terms, well, actually, if we multiply it in here, then all these other terms are going to vanish, and that leaves us with g of minus I omega. So once more, we go up here, and in fact, we are going here. Let's write this out a bit more clearly. So here, if we apply s equals minus I omega times y, then that term will vanish, leaving us with all this stuff. And then we apply here s equals minus I omega. That's going to leave us with minus 2 I omega. So that's retained there. And then in all this other stuff, that's going to be the same as g, right? Remember, this is g. And this is, we are applying s equals minus I omega. So it's g of minus I omega. So that's how we get our coefficient for A. Similarly for B, we multiply by s minus I omega to get rid of this one. And then we apply s equals I omega. So we'll get here 2I omega. And then this is g. And so we can just seek g of I omega. And so that's what we get for B right there. Then for C, again, we would multiply by s minus P1. So we'll write here s minus P1 for y. So when we multiply that through, then we can see here that s minus P will survive in all these other terms. And when we apply s equals P1, then all those terms will zero out, leaving us with just C. So we can say here C equals the limit when s goes to P1 of s minus P1 times y of s. So that's just the straightforward Heaviside partial fraction expansion that we've done before. So now we have a method at least for estimating these constants A, B, C. And so we can identify here that our eventual response is going to look like this, right? So we apply those constants in here, and we can invert each of these terms to give us the time domain solution. So inverting here, this is y of t. Inverting here, where a is this constant, this is going to be e to the minus I omega. So e to the minus I omega t, and then this thing is from this constant right here. So similarly for the second term, it looks like that, and then for the subsequent terms, of course here these are all s minus p, and so this is going to be e to the p t, and there'll be this constant in front of it, which we get in this way. So that's going to be our response. And now if our system is inherently stable, then all these p's will have negative real parts. right? It's basically saying it's not worth talking about if this is not a stable system. So to make progress, let's say our system is stable. So all the real parts are negative, and so as t goes off to infinity, these terms all zero out. And so eventually we end up with this relationship, right? Only these terms survive. And now we note here that we have basically a number, well, let's expand each of these first. So if we take g of I omega, we can say that generally speaking, that's going to be a complex number. So whatever g is, if we stick in this pure imaginary number, we will get out some, generally speaking, complex number. And that complex number will have a magnitude and it will have an angle, whatever those are. So this is general, that's always true. And then similarly for g of minus I omega, we will get some other magnitude and we will get some other angle. So we have g of I omega represented this way. And then comparing these two, we can say that, well, the magnitude of g of I omega must equal the magnitude of g of minus I omega, right, for complementary functions. So that's going to be the same. And then similarly, the argument of g of I omega must be the same as minus I argument of g of I omega. So being complementary, that will just reflect itself. So there might be some revision of complex numbers that's needed there, but you can show that. And so accepting that for now, we can say that if we make those substitutions in here, then we can see that we can group our exponential terms like so. So we can say both those factors g of I omega have this common magnitude g of I omega, which we can group out here. And the 2I we will take in underneath here as a denominator. And then the exponential sums, right, I and that, we can group together like so. And then if we consider this, we can see that this has the same form if we apply our trigonometric identity and our complex number algebra. We can see that this is nothing but g, the magnitude of g of I omega multiplied with the sine of omega t plus the angle of g of I omega. So we can translate it to this form, and again, do go back and revise your complex numbers to see that this is true. And then we can rewrite this, well, we can just divide here by the u over bar as a scalar. And so now we have this relationship. And so from this, we can see here that our response, our magnitude ratio, right, that's what this is. We have some amplitude of y, and if we divide that by the steady state value for the input, then that's going to give us our amplitude ratio or magnitude ratio. So that's there, and so clearly this is an oscillating part, so we don't regard that in terms of an amplitude ratio. So it's simply the magnitude here is going to be our amplitude ratio, and then the phase angle here, we can see our phase lag here. So that's going to be the offset time or the phase angle. So our phase angle is equal to this thing, which is nothing but the angle of the complex number g of I omega. So that's quite a useful and surprising result, that we can get the magnitude ratio at any applied frequency simply by evaluating for that function the value at I omega and taking the magnitude, and the phase angle is the same as the angle of g at I omega. Right, so that's a useful result, and we look at how we can use that in our Bode stability criterion. So given that we have this basic theorem now, we recall that our stability requirement is that the poles of our closed loop transfer function must all have negative real parts, right? So we got the poles by solving this equation. We said the poles were the zeros of this equation. And so clearly, if g ever equals -1, then this is going to be, we are going to be at the pole. And then if we have negative real parts, it's unstable. So the possibility for instability is when 1 plus g open loop equals 0. And so we can regard this as the point to avoid. And just be a little bit careful in how we read this. So in the last lecture, we were only talking about solutions to this equation. We said, well, behind this g function, there were parameters that related to the control equation. So we had parameters like kp, tau I, and so on. So the proportional controller constant, we were looking at different controller constants, and we were looking at what values of S gave us those controller constants. And then we were testing to see whether we had positive real parts. That was our stability check. So now we are looking at something different to that. Now we are looking at G as G is this S function. So we could, in principle, stick any value for S into G. But we know that if G open loop gets close to this number -1, then we are going close to the poles of G, and hence we are going into S values where we might start getting an instability. So we are regarding this value of -1 as a kind of a critical point. So we want to know what values of S get us close to -1. Well, that's when you go ahead and find the roots. So right now, we are going to change that. Instead of only looking at solutions to this equation, we will regard the plane of g of S as a plane of possibilities, and we look at how g traces itself out as we apply different values for omega. So we have now this basic theorem which tells us that g of S, that the magnitude ratio is equal to the magnitude of g at I omega. So we could say, well, we are concerned about this point -1. And in fact, we should, or we could write this a little more generally as -1 as the real part and 0 times the imaginary part, right? So this then implies to us in the plane, if we imagine a plane of axes, then just to the left of the origin, right, at -1 for the real part and 0 for the imaginary part, that there exists this critical point. So we know that that g of I omega magnitude is the magnitude ratio. So we want to know, how does the magnitude ratio look for our function at this critical point? So we would then say, well, if it's at that point, then the magnitude of g is going to be 1, right? This is the point -1 on the negative real axis. And so if g happens to be sitting at that point, then the magnitude of g must be 1. So never mind that this is on -1. The length from 0 to -1 is 1. And then the angle of -1 on the negative real axis from the origin is -pi, right? So if we have a 0 here and we are rotating around the 0, then we start from 0, go through pi by 2, and then reach -pi or pi here. So those are the critical values, those defined for us on the imaginary plane, this point that we might have some concern about. Right? And so a marginally stable system may be close or on this point of potential instability. So we define that to be the critical frequency. So we don't know yet what this omega might be, and we say that there will exist some omega value, some single frequency that is going to get us to simultaneously that magnitude and that angle. And so let's look at how we can reach such a point. We'll come back to this representation just now, but let's start plotting this out for different functions. And if we look in the notes here, we can see one simple function. If g is just a constant, if it's independent of s, then we will have a certain representation for that. If g instead is a first order decay type function, then we know g of s looks like that, and so on. So let's start graphing that out. And right here, I've written up some code to help with this. So here, importing the same libraries as before, and here I've created a list of equations. I'm just going to comment out some of these. So at the moment, we are looking at g being a single constant, and so we've written a function here which accepts three arguments, a, b, and c. And so a is some constant that we are going to send into this number. And we are going to calculate, we'll come to L and theta just now, but we are generating a set of complex numbers, and here we are setting a very small value. In fact, I think this works if we set that to 0. So we set s equals I omega. That means the real part is 0 and the imaginary part is omega. And we are considering omega logarithmically spaced from -2 to 2. So that's going to be 10 to the minus 2, 10 to the minus 1, 10 to the 0, which is 1, 10 to the 1, 10 to 2. So this is from 100th to 100, and using 1,000 points between those two values. So we are letting omega vary from a very small number to a very large number, and so we are plotting out our function. So once more, we want to know what g looks like if we apply different omega. So we are going from omega very close to 0 to a very large number. So we are looking at g of I omega, and we are looking right now for the constants. And the way we are doing that is we are creating an s value. So here we are running through all the omega values. We are looking up a current value of s, then we evaluate g, and then we go ahead and plot that in the real part and the imaginary part. And we can also plot that in terms of the frequency and the magnitude and the frequency and the phase angle. So let's just run that. And you can see here, g equals a, and a is simply a constant. So the real part of a is 20, and the imaginary part is 0. So that's g. There's no change in s. G is not a function of s, so it's just a point like that. And then the magnitude of g here, you can see it's 20. And then again, it doesn't matter what the frequency is. G is just going to be a constant number. And similarly, it doesn't matter what the there's no change in the angle for g. So g is a constant in the positive on the positive real axis, and so the angle is always going to be 0. So on a plane like this here, on this plane, we can imagine 0 is somewhere down here, and so from that 0 to this point, the angle here is 0. So the angle stays on 0 no matter what frequency we apply. So that's how G is varying with omega in this case. So that's a kind of boring result. Let's look at a slightly more interesting function. So now we have B over AS plus 1. So that's our first order response, right? So we are looking here. Let's space this out a bit. Okay, so this is the function we are looking at, and I'm using B and A here instead of K and tau. We'll see why just now. It's a general code that we can use for many other things. So anyway, I'm using B and A. I think it's B and A. It might be A and B. Yeah, B is the constant, and then A is the coefficient here, also a constant. And then if we apply our basic theorem, if we apply G of I omega, then it's going to be tau I omega, and we can multiply numerator and denominator by by the complex conjugate there. And so obviously down here, your I squared and that minus 1 will become a plus, and we get 1 plus tau squared omega squared. And then out here we have this factor that we have to multiply by k. So that's the magnitude, and so the magnitude ratio then looks like this. And the angle then is going to be the arctan of the. In fact, this is the wrong way around, right? This should be imaginary part over the real part. Imaginary part over real part. Okay, and if we look at the imaginary part here, we have inside here, we've converted it. This is G, and the imaginary part is going to be tau omega over 1 plus tau squared omega squared. The real part is 1 over 1 plus tau squared omega squared. If we divide imaginary part by real part, the denominators will cancel, leaving us with tau omega over 1. So it looks like that. And sorry, that was minus tau omega. So minus tau omega over 1. So that's our first order lag. And let's see what that looks like. So we've applied that there. We run this. And you can see here, okay, let's not use distracting values. I'm just going to use 1s for A and B. C's doesn't feature at all. So it looks like this, right? If we go back to the equation, when omega is close to 0, then this is basically k over 1, so that's k. So if k equals 1, then the magnitude ratio at omega equals 0 equals k. In our case, we applied 1, so that's right here. So this is the point that we start out at. And then as we increase omega, we can see here that the denominator will increase, so our magnitude ratio will decrease. And the angle here is going to become more negative. So our magnitude is decreasing, so we are moving in towards the 0, and the angle is decreasing as well. And in fact, those two things together will cause our curve to curl in like that. Right, so that's what we get for the first order form. And now instead, if we want to plot the magnitude of G as a function of omega, so if we want to plot this instead, you can see here that as omega increases, this function is going to decrease. So G starts out here and just decreases in this way. And similarly, we said as omega increases, this angle gets more negative. So it gets more negative and flattens out a bit, but it's still going negative. It's tending towards minus a half pi. Right, so that's the graph of G of S. And the point of this is we wanted to estimate how close or how far we are from the point -1, 0. Well, this is the clearest place to look for that. -1, 0 lies out here, right? Here's the real numbers. Real numbers start from 0 here. So -1 is here, and then imaginary part is 0. So the point is here somewhere. And so we can see for the first order lag, there's no way for us to get closer to this point, right? As we increase our frequency, we get closer and closer to this point. So we are getting closer to this point here, but it's not as if this is going to expand in any way to touch the -1, 0 point. So we can see that this is going to be quite stable, and we can even say that, well, the closest I get to instability occurs perhaps from this region on. So if I'm really afraid of instability, then I might want to stay away from these types of frequencies. And of course, later on, we'll see that staying away from this range of frequencies translates to staying away from a certain range of parameters, of control parameters, and so that helps us to design our controller. So that's what we can see here. However, in a way, these are not so easy to work with, because we have to kind of imagine what's going on in 2 dimensions and working with imaginary numbers and so on. And so instead of this, we have these nice definitions. So Bode was one of the researchers who spent a lot of time developing better controls methods, and one of the tools he used was this definition for the log modulus. So we define here the log modulus as taking log to the base 10 for our magnitude of g of I omega. So 20 times the log modulus of that is defined as L. And then for theta, that is the phase angle, so no change here. But on a Bode plot, instead of we plot L against the log of omega, and we plot theta against the log of omega. So those are the other functions we can see here. So L versus a log of omega looks like this. So it's 0, and then it drops off to what looks like a straight line. And here also for theta, it's 0 for a while, then it drops off in what looks like a straight line, and then it saturates out, so it's going from 0 to -π/2. And then we'll see later there's another plot we can also do. Instead of taking L against log of omega, we can plot L against theta. And so we could plot it like so also. Well, it's that way. So that's another plot we can do. So anyway, let's go back to g being constant. So if we apply g as a constant here, we said g is just a point here. It's a constant. G of omega is a flat line like that. So if the magnitude is not changing, then L, which is just the log of that magnitude, that's not going to change either. And then here we said the angle is also going to be a 0. So we are always pointing from 0 to g. And so that angle is always going to be 0 there. Now we had set a equals, g equals a, so that's a real number. If we increase that, we can see here that obviously our magnitude of g is going to rise, and it's going to be equal to that value. The angle is not going to change, because this just means we are moving further away down the real axis. The angle is staying the same, right? Pointing still straight back to the origin. That angle hasn't changed at all. So the magnitude shifts, the angle doesn't shift. And then L will shift, right? L is the log of the magnitude, so that will shift up. Here the angle we said is not changing. And if we plot this, here we have L against theta. For a given value of A, neither L nor theta are changing. So this is also just a point, right? So that's how it looks when when G is just a constant. And by the way, we could have made an imaginary number also. Then we would just have some imaginary part, and the angle won't be 0 anymore, but it will be some constant number. I'm just thinking, okay, I don't think I can do it here. Let's do it here. Let's just say S equals complex, and we'll set a real part of 3 and an imaginary part of 1. And now you can see here the real part is 3, the imaginary part is 1. Omega is the magnitude is 3, and it's not 3. The magnitude is now the square root of 3 squared plus 1 squared, which is that. And then the angle is no longer 0, right? We have a positive imaginary part, and so theta is shifted above its value. So here's our value of G, and our origin is down here somewhere. So the angle is some non-zero value now, which is there. And then L and theta and so on are like that, so non-zero values here. Anyway, let's just put this back as it was, right? And so that's the complex, that's the constant function. And then for our first order lag, right, for our first order process, we have talked about this already. And now, if we plot it out for L, well, we've also talked about this, right? So that's L as a function of omega, theta as a function of omega, and L against theta. And in the notes here, we can see, well, this is back when I was doing all this in MATLAB. So if you like MATLAB, you can also look at this code instead of the Python code. Then if we have a first order lead, and those terms lag and lead, they have some meaning, which we'll talk about a bit later. For now, it's B times A times S, right? So BAS plus 1, B times AS plus 1. And here we have that, let's just run that. We have here that our real part is a constant, and our imaginary part is changing with omega. So let's think about the function again. This is our G function. You can see the real part is constant, right? Remember, we are applying S equals I omega. So it's only going to affect this part here. So omega goes with the imaginary part here. It's not going to influence the real part. So the real part is constant on 1, and the imaginary part is varying in omega and tau. So here we are just increasing. So as omega increases, our value for the imaginary part increases. So our magnitude is going to increase over time. Remember, our magnitude is going to be from the origin, which is somewhere back here. So it's this length and this length, and you can see as we go further up this line from the origin, that's an increasing magnitude. So as we increase omega, our magnitude is rising. Also, if we are looking from the origin at all these points, we can see the angle is also rising. But eventually, right, if we imagine this line going to an infinitely great distance, then in effect, it's tending towards a vertical line there. So that vertical line is going to be at an angle of pi by 2. So we rise from 0 to pi by 2. So it's going from 0 up here, and you can see pi by 2. So our angle is going to steady out like that. And we realize that this is not a linear rise here, at least not down here. And we can see that a bit if we limit our range in omega. So let's do this over a much lower range. So if omega changes over a smaller range, you can see it's a curve here. So we said that the magnitude was the distance from the origin to this point, and so on. You can see that with a linear rise here, the magnitude is not going to rise linearly, right? But when you get to much greater distances, then that effect is smaller, and so it starts to look linear after we go far enough. So let's just put this back to 2. So instead of plotting it this way, directly magnitude against omega, if instead we plot it as L, which is the log of that magnitude, against the log of omega, then we hardly see that change, that small change down there, and then we see that it's rising with a fixed gradient here. So for the first order lead, it goes up like that. And then the angle, again, we are looking at the origin somewhere here, and then it's pointing initially at the 0, and then slowly it will rise, and then as we get to much greater values, it's effectively looking from the origin straight up. So that's going to be an angle of pi by 2. So it's going from 0 to pi by 2 now, and we can see that here, 0 to pi by 2. And we can compare that with the earlier case. We said this was the first order lead. If we look at the first order lag, by comparison, L started at 0 and it fell down that way. In comparison with the lead, L starts at 0 and goes straight up. And then for the angle, we had that the angle starts at 0 and falls to minus pi by 2. In the case of the lead, the angle starts from 0 and goes to plus pi by 2. So you can compare the first order lag and lead, and you start to see why they are given the names that they are. It also has to do with the associated time functions. When we read a function like this, we read this as an exponential die-off. We happen to know that we often get a negative value and so we get an exponential die-off, whereas this tends to be an exponential increase. So that's again why it's lag and lead, but you'll acquire that experience as you do more of these examples, and this is terminology that's developed quite naturally, and it kind of grows on you also. Let's look now at delay time. So if there's a delay, we saw before that we would represent that as e to the minus tau s. And so if we go and graph that out, you can see here that I have to use the NumPy library to access the exponential function, and I'm using that constant a as my constant, and there's my s. So if I graph that, you can see here that G actually looks like a circle, and for the magnitude, you can see here the origin is at the center this time, and the distance is always a 1 here. So if the distance is a 1, then the magnitude of G is constant and 1, and so no matter what frequency we apply, our magnitude is staying fixed at 1. So we can see that here for all frequency, even though G is not a constant this time, the magnitude is a 1 always, and so we get a fixed number like this. Then in terms of the angle, well, here it all depends how fast you move that angle around, right? All angles are going to be possible. So 0 to 2 pi, anything in the range 0 to 2 pi, or pi to minus pi is all fair game. And you can see that here, that I've logarithmically spaced my points out. So we are getting the scatter in that range. So all angles are possible, and it just depends how you've discretized your angle, or how you've discretized your frequency. We'll see there's a slightly better plot of this in the notes. Now, if our magnitude is unchanging and it's a 1, then that's going to give us a 0 for L, right? Log of a 1 is a 0. So we get a 0 everywhere here. This minus 1, it's a bit deceptive. This is on the scale of 10 to the minus 15. So this is just a consequence of simulating this on a computer that has some numerical error. So this is in effect a 0. This is all a 0. So so just because we might have some values that are accidentally, because of the rounding off error. So if the accuracy is 10 to the minus 15, anyway, that's all a 0, right? So similarly here, if we plot the angle against the log of omega, and we know that's a scatter between pi and minus pi, then we get something like that, and then we can plot that one as well. So this is done much better if we think about it more carefully here. So we said that's a 0, and we can say, well, our theta is varying from that 0 down in that way. So that's our delay function. If instead of that we have powers of s, so if it's s to the power n, then, so in Python that's how you say to the power. So in some languages it's like that, in Python it's like that. And so s to the power a, if we run that, as you increase s, you are going to change the angle there. So all the plots are shown there, and maybe it's a bit better to look at it here. So for a given value of n, you are going to get omega to the n, I to the n. So depending on whether that n is even or odd, you will oscillate between plus and minus. And then depending on that value, g will be omega or omega squared, and so if you imagine putting that in the log, so log of omega to the n is equal to n log of omega. So that number n is going to show up as the gradient of our line L as a function of omega. So that's what we can see there. Okay, and clearly the angle is changing, so the angle is changing with n, but it's not varying with omega itself, right? This time, omega is changing only the amplitude, it's not changing the angle. So the line, the angle of the line is fixed with respect to omega, which means that the angle is fixed with omega. So we get, so as n changes, the angle will change, but with respect to omega, it's a constant, right? So that's what we get in that case. So here is shown for n is minus 2, minus 1, 0, 1, 2. But of course you can look at in-between values as well. Okay, something a bit more interesting now, looking at the second order underdamped lag. Here we have the second order underdamped lag, and well, it looks like that, but let's look at the way we set it up here. We note here that B is our tau, right? B is tau. Remember, for the second order underdamped lag, we chose to write it in this form. So we set tau as B, A as Kp, B is tau, and C is zeta. Right, so here you can see C is in the right position. It's zeta times tau, and so if we change C, that's going to change how damped our response is. So let's look at that here. So there's a bit of development. You can work through the algebra and see that L looks like this. And so for low values of zeta, we start to see some peaking happening. So let's apply that here. So let's use 0.1. And you can see here, you get that peak appearing. And of course, the smaller you make the C value, the sharper that peak will become. So you can make that arbitrarily large by choosing C small enough. And that then is a point of concern for us. We want to limit how far that's going to go, so we can pick a value of zeta that limits the maximum amplitude ratio. So that's again an application of this type of graph, right? So we can limit it just because we don't want those kinds of oscillations, or we can say, well, we are concerned about how close this function is getting to the -1, 0 point, and so we can look at this function here, and you can see -1 is somewhere here, -1, 0 is somewhere here. So this function never actually goes that close to the point of where there are poles, and that we have to worry about this. But anyway, we might want to limit this so we can control that with our zeta. And again, we know that behind the zeta there are control values that we have to be concerned about, and so on. So that's the second order underdamped lag, and we can use these planes to navigate that. Now, a useful property of the Bode plot is that we can add together functions in series. So remember when we did the two tanks in series problem, we had that the overall transfer function was the product of the first and second transfer functions in series, right? And if that's the case, then the magnitude of our resulting transfer function is going to be the magnitude of the products there. And so if we seek the log modulus of the overall transfer function, that's going to be the log modulus of the product of those two functions. And of course, if it's the log of a product, then that becomes the sum of the logs. So the log modulus of the first transfer function plus the log modulus of the second transfer function is the log modulus of the overall process. So that's quite useful. That means we can just add together our curves for the various functions. And we can do that in a case like this where we have tanks in series. We can also think about what if we have just different functions multiplied together. If we have some complex function f of s, so if that was the first function f of s, and if we have that multiplied by some other function f2 of s, f1 of s and f2 of s, if we had the product of two functions like that, well, if we don't know how to plot the whole function in one go, we can break it down into simpler functions, because now we've got all this experience looking at these individual transfer functions. And so that means we can plot individual lines on our S log omega graph and just add them together. And that's what we are saying here. If we have transfer functions in series, then we can just go ahead and graph each transfer function independently and then just add them together graphically, and that will give us our overall behavior. Similarly, for the angle, we also show here that in terms of that complex number, if we can represent that as the as the product of two complex numbers, then when we group these together, we can see that the phase angles add together. And this is a consequence of choosing pure complex numbers, right? If we don't have a real part, then it's easy to just add together the complex parts. and so our angles are just going to add together as well. So that's one of the great advantages of Bode plots. So once more, the Bode plot is where we plot L against log of omega and theta against log of omega. So that pair is a Bode plot. And if we have individual transfer functions, then we can just add them together and get the overall transfer function. And then from looking at that, we can think about whether or not we are going close to the -1, point. So some of that is shown here. Okay. I thought there was something. Okay, I guess we get to margins just now. So anyway, that's adding together transfer functions. Then on Nichols' charts, we have already seen this. That was the 6th little subplot we had here. So instead of plotting as a function of log omega, if we took L and plotted it against theta, then we could plot this. And I know it looks like, oh, we've just gone and made every possible permutation of all the graphs that we have. But no, we will see that through a special mapping, this graph actually becomes quite useful in terms of designing control. So anyway, for now, we will just say that it's L against theta. So on our Nichols charts, we can read off values for L and theta, and we can graph out the curves that we get there. So here, I guess we are just plotting all those different functions we saw before. So for the first order lag, it goes down like that. For the first order lead, it goes up like that. For the delay function, we get something moving in from 0. And for the for a delay together with a first order lag, so for these two together, it turns out to do that, and so on, right? Yeah. So we can view things on the Nichols chart. So for now, we won't say too much about this one, but this will turn out to have some very important applications in a little bit. Once more, we have said all this. The Bode stability criterion. So we know that our poles of our transfer function, of the closed loop transfer function, are at the zeros or at the roots of 1 plus the open loop transfer function. So the point -1, 0 is the critical one for us. And in terms of polar coordinates, that's the point where the magnitude is 1 and the angle is -pi. So if we are looking on the origin, do I have an origin somewhere? So here, if we take here's the origin, right at 0, 0, there's the origin. If we want the point -1, 0, so -1 is somewhere there, and 0 is there, so that's the point we are concerned about. So we want to know how close are we going to this -1, 0 point, because that's where our poles reside, and that's where we might get caught out with a positive real part or something like that. So we want to know how far is our system staying away from that point. Right, and here is a nice way of estimating that. So we'll find the Bode plot quite useful in this regard. So we've identified this point, and we are asking on this graph here, where is, or how far do we manage to stay away from that point? So if we think about it, at that point, the amplitude ratio is a 1. So if we look here for the 1, then we can say that at this frequency, we are a little worried. So we've got a 1 here. And then if we look at the angle, yes, we are close to -180. So it looks like this function is passing fairly close to that point of instability, of potential instability. And in fact, here's a nice example. So let's graph this one out. 2 over 0.5 s plus 1, and this is cubed, you see. So I'm saying this is a nice example because in all the examples we've looked at so far, we were pretty far away from -1, 0. So let's now use that, that transfer function, which I've already set up here. And graphing that, not sure about my constants, whether these matter right now. Right, if you look here, -1, 0, you can see there's 0, so -1 is somewhere there. -1 and 0, so that's somewhere there. So the function is passing in this way, right? You can see that this function is positive here. And so the worry to us is that what if we increase, if, for example, we are using a proportional controller, what if we use values that cause this to wrap around there? So if we were applying a proportional controller to this process, we would have a kp multiplied with all this, right? And that's shown here, right? We may have a multiplying factor in here. So let's simulate that. And we have done that already by specifying that it's a times that. So there's our kp. So as we increase a, we shift this curve around. At the moment, it's not that close to -1, 0. -1 is somewhere here. Now let's increase the value of a. And I'm just going to do that here. So let's increase it to 3. And you can see now -1 is sitting here. And so we are getting close to that point here. And in fact, instead of poking around on this graph, let's rather look here. -1 is at the point of 0, right? So 0 here is at a frequency in this range. And then if we look at our angle graph in this range, it is close to -pi. So definitely we are getting close to that -1, 0 point. And in fact, if you analyze that equation properly, by that I mean doing the numerical work, you find that at a value of 4, definitely you are at that point. So you are crossing over -1, 0. You are in and amongst the roots of this equation, and so you might be heading into instability for a kp value of 4. So that's where it just starts to go critical. And let's exaggerate that. Let's try 20. Now you can see we are all the way to -10 here. So this has the x-axis has scaled here. So -1 is somewhere here. So now we are definitely circling that point. So we are definitely in the zone of instability this time. So the limitation for us is a 4. We don't want to stray to more than 4. And in fact, for safety's sake, we want to maintain some margin away from that 4. And talking about margins, it's quite nicely illustrated in this example. So here's a case where we are plotting the amplitude ratio as a function of frequency. And we know we are concerned about an amplitude ratio of 1 and an angle of -180 degrees. And if we look here at a 1, that's the frequency that we have. And then if we look down at the angle, that angle is more like a -90. So there is a good, and -180 is here. So there's a good margin between the angle of concern, which is -pi, right? So when we are pointing down the negative real axis. So there's quite a good angle between that point, right? The point when it's 1 and the angle. I think there's a nice figure for that here, right? We are saying basically that the point at which our graph becomes a 1, right, is here. And now this graph is not the same one here. In terms of this this picture, the angle, it turns out when this graph G equals 1, that the angle happens to be quite far away from minus pi. So in this case, there's a nice margin in terms of our angle. And so that's talking about it from the perspective of staying away from, staying away from the angle. But if instead of starting with 1 here, let's say we consider now this minus 180 degrees. So we know that along the negative real axis, we are concerned about 1. So we can say, let's look for that angle of minus 180 degrees, and then look at what the magnitude is. And we look up here and we can see the amplitude ratio is a lower value or where it cuts the negative real axis, and we only cut the negative real axis here at 1. So in this case, we have a margin, a magnitude margin, if you like, of that distance. So in both cases, we have a fairly significant margin. So we stay away from the minus 10 point fairly comfortably in this example. Right, so that's how we can look for a margin of safety in staying away from potential instabilities in our systems. And so we can represent it that way, but we can see that it's a little easier to see in terms of the Nyquist plot. So instead of looking across two different graphs and saying, oh, maybe there's a margin here, then how's the margin there, and then when that's that value, where's that value? Instead, we can just look here on the Nyquist plot and say, there's minus 1, 0. How close does my transfer function ever get to that? And we can imagine a kind of circle around there and say, well, that's about as close as we get. And that's then quite clearly the margin of importance for us. Right, so we have these three ways of looking for our margin. We can look directly on the plot of G, we can look on the Bode plot, we can look, we said Nyquist, and then Nichols we'll look at just now. Okay, so that's those are margins of stability. Right, and then the same concepts here, the gain margin, so how far are we from minus 1, so and how far are we from the minus 180 degrees, so producing the lines and so on. So you can read through this in more detail. Right, as we said, Nyquist plots, imaginary part against the real part, and there's nothing really new for us here. But you can go ahead and read this stuff and how to plot it. So you can think about asymptotes and nice things like that, and how the function wraps around. So for first order lags and first order leads and all those usual things. We have said this before, right? We said for a first order lead that the real part was constant and the imaginary part was changing with omega. So we've already looked at all this stuff. We now come to quite a beautiful line of logic in the field of controls theory. And it's quite a simple line of logic, actually, when you follow all the arguments carefully. So do please work through these arguments, and this can all be understood in terms of the fundamentals. And this is really the basis upon which all our controls design is going to be based. So let's work through this. We know, first of all, that if we have any root of the characteristic equation in the right-hand plane, then we are going to have a positive real part, and the system is going to be unstable. So this is the great concern for us. Is the control that we implement going to cause our system to have a positive real part? And we have been talking so far about getting close to the minus 1, 0 point and so on. And we haven't fully motivated that. Right? We've been talking about a phase margin and its closeness to minus 1, 0. But we haven't shown rigorously that this is the point that we need to consider when trying to decide that we have stability. And we gave some some kind of weak arguments in that line. And now we are going to establish rigorously why this is the right criterion. So in complex theory, there is this principle of the argument theorem. So according to this theorem, if you have some complex function f, and if it has z zeros and z poles in some domain of the S-plane, then the number of encirclements of the origin of that function f, the number of encirclements that it will exhibit, will equal the number of zeros minus the number of poles. So once more, according to the principle of the argument, and we are going to look at the proof of that. That's another quite visual, easy to understand proof. Right? According to this theorem, the principle of the argument, the number of encirclements that f is going to make of the origin will equal the number of zeros that f has minus the number of poles. So the number is, so if you have 3 s values where f goes to 0, then you have z equals 3. And if you have 2 values of s where f goes to infinity, then you have 2 poles. So the number of encirclements of the origin for function f can be deduced by taking s and having that encircle the region of interest. So if we want to know how many zeros and poles in some domain of S, so if you imagine in the S-plane some boundary, so inside that boundary, how many zeros or poles are there? Well, you just encircle that boundary. You just let S vary over that whole boundary, and you apply all those S values in F. So as you travel around the boundary, applying all those values of S, if you observe the output of that function, if that function wraps around the origin n times, then that value n is going to be the difference between the number of zeros and the number of poles. Right? So that's the principle of the argument. And now in our application, we are dealing with the function 1 plus g open loop. So in our case, our interest is in the number of times we encircle minus 1, 0. So rather than the origin, we are worried about wrapping around minus 1, 0. And that's because we want to know how many zeros do we have of this function. Right, so we have, this function. Right, if I'm writing it as a plus 1 there. So if we have 1 plus g open loop equals 0, then this is the point of interest. And then if we want to know how many times we wrap around the minus 1, 0 point, then we are concerned with the number of encirclements there. And so we want to know how many zeros of this whole function do we have in the right-hand plane. And so if we accept that for G open loop, we don't have zeros, we don't have poles, right? Then that process is open loop stable. And that's what we've been talking about, right? That G open loop, right? We are only concerned about the closed loop being unstable. The closed loop is when we add in our control and we look at the difference from the set point. So in terms of the closed loop, we don't want poles. We don't expect or accept poles in the open loop version. So before we implement control, our process must be stable, right? We are not considering that something is inherently unstable and then thinking we can make it more stable. So we are not talking about something that's open loop unstable already. So we don't have for G open loop any poles, right? We are only concerned about zeros of the closed loop transfer function. And when we talk about closed loop, then this is the point of interest. So if we don't have any poles in G open loop itself, then P equals 0. So P equals 0 for this function. And of course, actually, we are talking about G open loop plus 1. Well, the poles of G open loop is going to be the same as the poles of 1 plus G open loop. Remember, a pole is where G open loop is going off to infinity. If you add a 1 to that infinity, that's not going to break the bank, right? That doesn't make a difference. It's not going to shift where our pole is going to lie. So we can say that if we know this is going to have 0 poles, then this whole function has 0 poles. So if there are 0 poles, then the number of encirclements is going to equal the number of zeros. So for our closed loop function, the number of times that we encircle minus 1, 0 is going to equal the number of zeros of this equation. So if we have any zeros of this equation in the right-hand plane, then we have an unstable situation. So we want to let S vary over the entire right-hand plane. And if we find that we encircle the minus 1, 0 point, then we know that we have instability in the system. Right? And in fact, that's what we have been using up to now. We have been worrying. I have been talking through this lecture as if I'm worried about going around minus 1, 0. And we could sort of agree that, yes, if we cut through minus 1, 0, then we might be at a root and there might be instability. That's how I've been saying it. And I was a little bit misleading there because I didn't want to get into all this just then. But now we are at the point where we actually need to justify ourselves, and we have already been talking about encircling minus 1, 0. And here's the proof that that is our concern. Right, so once more, the principle of the argument is that if we observe our encirclement at the origin, and if our poles are 0, then the number of times we encircle that origin equals the number of zeros there. And if we choose the encirclement to be around the entire right-hand plane, if we let S be around the entire right-hand plane, then our function here, 1 plus G, if that function, the number of encirclements by that function is going to be the number of zeros we have for that function. So we then want to consider the encirclements of minus 1, 0, and the encirclements of that point will tell us how many zeros we have in the right-hand plane if we let S vary across that right-hand plane. Right, so that's what we need to do, and that's all further described here, so you can read it a bit more carefully. But before we go ahead and try that out, we still need to motivate ourselves, right, for this to be really rigorous and for us to really say we understand why all this works. We do need first to motivate this, right, this mysterious statement, this principle of the argument. Can we prove this is true? Can we prove that if we choose some region and if we encircle that region, that the number of encirclements of the origin equals Z minus P? Well, let's look at that. Here's it's quite a nice simple proof. So here is an example. We have arbitrarily chosen this region in our S-plane, so imaginary part of S and real part of S, and we've chosen this as the boundary. And so we are going to talk about moving around this boundary. Now let's say it was true that yes, we had this 0 inside of that boundary, and we had these two poles, we had these two zeros and we had this one pole. Right, let's say that's what our function had, right? So remember, we are considering the zeros and the poles of some function. So if we have those two zeros and that one pole, then clearly our function looks like this, right? S minus the 0, so at those values Z1 and Z2, when S equals those two values, then it goes to 0. Clearly that's true, and clearly when s equals p1, then that's a pole. So we have the 2 zeros and the 1 pole for f. Now, of course, this is going to be a complex number, and we can construct for ourselves the angle of that complex number, the output to this function. We can say the angle of f is going to be the angle, right, just by substitution, is going to be the angle of all this. And then just a few minutes ago, we said that if we convert this, if we use the exponentials, and we can see that producting exponentials is adding them, and then by difference we can say dividing by the exponential is subtracting it, then we can say here that the argument of f, the angle of f, of that complex number that comes out with f, the angle of that is going to be the angle of s minus z plus the angle of z minus z2 minus the angle of s minus p1, right? And so we can almost see the proof already, right? Let's pick a point. Let's take the highest point as our starting point, and let's think about just this 0 here. Now, as we travel around this s, you can see we are going to encircle that z completely. And so if we were tracking the angle, so imagine here an axis, right, a horizontal coming out of z1 like that, and then the angle between that line and the point or the line from z to the boundary. So now as we rotate that around, you can see that angle is shifting, and that angle is going to go completely around z1. So going around this boundary is going to increase the angle of f by 2 pi. And similarly, it's going to increase the angle of f by another 2 pi here, right? So that's 2 pi plus 2 pi. And then the pole is, there's a minus sign in front because it was in the denominator. So for the pole, it's going to have the reverse. You are going to get minus 2 pi from this pole. So that's how we can find the number of encirclements. We can say that's 2 pi plus 2 pi. So we are going to go through 2 pi, then we'll go through another 2 pi, and then we are going to go through a reverse of minus 2 pi. And so we are left with the total number of encirclements, which is 1 for this system. So you see, it's quite a nice visual way. It's not exactly a proof. It's not formally shown that way, but we can see this must be true from this simple argument. So now we have what we need, right? We have said that if we can encircle the entire right-hand plane, then we can, and if we know the number of poles is 0 of G open loop, then the number of zeros of this function must equal the number of encirclements of this function, and the number of encirclements of this function is the number of encirclements of minus 1, 0 of this function, right? Now, a remaining question that you might have is, well, how am I supposed to go and encircle the entire right-hand plane, right? I want to know how many zeros I have in the right-hand plane. So I want to know any real number that's more than 0. Do I have any numbers like that? So to find that out, we have to encircle. It's not a nice boundary like what we've drawn here. We need to go and encircle the entire right-hand plane, right? I can't even draw it like that because this is going off to infinity, right? Even up here. So we need to find a boundary. We need to propose a way of drawing out the boundary so that we encircle the entire right-hand plane. And the way we do that is, right, we've already been talking about s equals I omega. So in the s-plane, if we are talking about s equals I omega, then we go straight up this axis. And so simply if we let omega go off to infinity, and we've already been working with large values for omega. If we let omega go off to infinity, then we are out there somewhere. And if we imagine the semicircle, so maintaining omega or maintaining an amplitude of infinity, then we just rotate the angle around until we're pointing straight down here. Then we'll be at minus infinity. and then as we let omega go back to 0, then we come back into the 0 here. So once more, we start at 0, we take s equals I omega and let omega go from 0 to infinity. So we go off to infinity, and then we start applying a real part. So we slowly increase the real part of that s value, and then we start reducing the imaginary part. So we go around like this until we reach minus infinity here, and then we reduce the value of omega until we come into the origin again. And in that way, we will have encircled the entire right-hand plane. And we have an example of that shown here. Let's just look at the blue line here for now. So this is a line that was generated for a given function. I seem to have lost it somewhere, but I have we have generated the output by letting s go from 0 to some arbitrarily large number. Of course, in the real world, we can't apply infinity except symbolically. So we just used an arbitrarily large number, and then we varied the angle so that it went around, and then we reduced it again until it came back up. And this is what we got for a kp value of 5. So the function wrapped around, and it came in, and that was the function that we had. Here's the point -1, 0. You can see it's not wrapping -1, 0. And so we have no encirclements of -1, 0, and hence we have no zeros in the right-hand plane for that value of kp. And then here, if we increase kp, we find that the function goes underneath and then around and then back around and looping like that, and then comes to rest there. And in fact, it's then a question to us when a function wraps around twice like that. It's not completely clear to us whether that function is wrapping -1, 0. So we could argue, well, what if the function is doing this? What if it's skipping over -1, 0 here, circling around, and then skipping under -1, 0? So in that case, it would be a stable system. However, in this case, it's actually not. You can see that -1, 0 does belong to the area encircled by this trace. So that's how you can generate your number of encirclements. And if you do this enough, right? If you try enough examples in this, you will find that this is symmetrical, right? So quite often we get the complex conjugate when we solve these equations. So you'll find, for instance, here that it will encircle, will swing around, and so as s goes from 0 to infinity, we'll find that we start here, we swing around, and we end up intersecting there. And then when we are out at infinity, and the amplitude is at infinity, and we circle around, we tend not to have any change. That tends to be a 0 contribution, because the denominator being infinity, that's a 0 contribution. So we tend not to have any contribution from the circling around. And then when we reach -infinity and progress in from infinity to 0, we tend then to generate the other side of that curve. And so we get a symmetrical picture that is traced out. So we can say then that, well, instead of doing things where we go off to infinity, circle all the way around, and come straight back in, it looks like we get all the information we need just by going from 0 to infinity. So because of the symmetry, it turns out that s equals I omega, where omega goes from 0 to tending to infinity, it's good enough just to look at that. And so that's what we've been talking about from the beginning here, right? When we started out in this set, we said we are interested in S equals I omega, and that's because we always knew this is what we were going to do. We always knew that we were just going to go from naught off to infinity, and just observing what happens there would be enough to observe how many times our function was going to encircle minus 1, 0. So that's the complete logic in trying to estimate the number of zeros in the right-hand plane, and hence the possibility, and hence assessing for the possibility of having instability. And we see that instability creeps up on us slowly. So Kp is 5, and then as you increase Kp, your system suddenly has strayed into a positive real component. So we would rather, instead of this being a yes or no question, are we unstable or not, we would rather estimate what's the critical point at which we are at instability. So what's the value for Kp where we are just going unstable? So what's the value of Kp that causes the point here to just start touching this minus 1, 0? And we do that through these concepts of gain and phase margin, which we've been talking about to some extent here already. Here, in this early example, when we were talking about looking at when is it minus 180 degrees, and then when is it 0, and what's the difference there. So that was all about how far we were away from minus 1, 0. So now we have the full justification for doing that, and here are some definitions that are useful. So we can define the maximum closed loop log modulus, and here we can see some examples where that margin that we talked about earlier was possibly not the best definition for us. So here, if we look at this transfer function, you can see it actually passes very close to minus 1, 0. So it's very close to wrapping minus 1, 0 and the system being unstable. And yet, if we apply the criteria that we described earlier, we can see here that we are at a magnitude of 1 at this angle, which is quite a significant angle. So if we just went by the phase margin, the phase margin alone, this would look like we have a wide margin, whereas in fact it's not a wide margin. So we have to look at both simultaneously. We would be able to see from the magnitude ratio that we are quite close, whereas if we just looked at the phase margin, we wouldn't seem to be quite close. And then the reverse is true here. Here we can see that the gain margin, the magnitude margin, appears to be quite far from minus 1, 0. But we can see in terms of the angle, because of this very shallow angle here, that we actually do pass quite closely to minus 1, 0. So in both cases, we would be able to detect that we do in fact pass close to the unstable point if we look at both criteria. So here we should be able to detect that the phase margin is actually too small, even though the gain margin looks pretty good. And the reverse, as we said, is true here. So we can just do it that way by considering both those numbers instead of trying to estimate it from just one number. The alternative to that is instead just plotting the closed loop transfer function. So instead of trying to estimate from specific arrangements of the open loop or specific characteristics of the open loop, if we instead just go ahead and plot for ourselves the closed loop transfer function, then we can see at all stages how close we are to that minus 1, 0 point. And so that's the basis of the closed loop contours on our Nichols chart. So the Nichols chart is it's the log modulus plotted against the phase angle, and And so the numbers on the grid are the so-called open loop version. So we have if we choose a point here, right, minus 60 and minus 12, then that's an open loop minus 60 for theta, and that's an open loop minus 12 for the log modulus. However, we also have these other contours. You can see these solid curves here. So those and these dashed lines. So the dashed lines are the closed loop log modulus, and the solid lines are the closed loop phase angle. And so if we choose a point here, we said minus 60, minus 12, then we can say that's equivalent to a closed loop value of perhaps minus 14, minus 14 for a closed loop log modulus. And then looking at the angles, that's something like a minus 50 closed loop phase angle. So we can go ahead and just construct a plane that has all this information on it. And then we can draw in our own transfer function. So for our process, we go ahead and look at just the open loop parts. And so the diagram that we showed earlier, we used this code to draw our plane, this one. So here, where we were applying all our transfer functions, and then we plotted all these graphs, and here's the one of interest now. And we had said back then also, don't think this is just a permutation. We are seeing now the power of this specific graph. So we have plotted here the open loop version. So if we go ahead and graph these lines, so we've got our lines drawn out here, then we can look simultaneously and see what the closed loop version of those lines are. So if, for instance, we pick a point here, then we can read off the closed loop values. And if we look along the curve, we can see in terms of closed loop values how that's varying. And we then can easily estimate how close we are to the -1, 0 point, right? So looking at that curve there, for instance, and then we can pick a contour and we can say, well, I want to always stay at a margin of -4. So if my process looks like this, I'm going to change Kp and I'll increase Kp until my curve just touches this other curve for -4. And then I'll know that's the maximum Kp that I can tolerate if I want to maintain that difference from -1, 0. So that's the power of these Nichols charts. And that's pretty much it. Down here, we just look at deriving those curves. So we talk about if it's a closed loop function, then it looks like that. And so we can establish the relationship between the closed loop values and the open loop values. And so that's how we can plot these charts out. And we will look in the tutorial space at using all these charts and maintaining our phase margins and gain margins